Okay, we're on chapter 9, polynomials, and it's called iterative methods. I'll write that out later, but what we're doing is estimating roots. Now, when you see a polynomial like the one that you can see up there on the board, how many roots does this polynomial have? What does it mean as well? Yeah, it means how many. So, yeah, the roots are where it cuts the x-axis. So there are 1, 2, 3, 4 roots. And how do we normally find the roots of a polynomial? By finding you factorize it. You factorize the polynomial and you put it equal to 0 and you end up with, you factorize it, put it equal to 0, and then you end up with the 4 roots, okay? Now, in other words, in some cases we can find the roots of the equation by using algebra. In other words, we find one root, we find the other roots either by factorizing or doing the long division into the polynomial. Then we can end up finding those 4 roots. Now, for example, you might be asked, this is just a quadratic equation. So find the exact roots of that quadratic equation. If you can't factorize it, if it's a quadratic, you just use the quadratic formula as they've used there to find the roots. Is that okay? So x is negative b plus or minus, etc. All right, so the roots there are 3 plus root 5 on 2, 3 minus root 5 on 2. See, we've got 2 roots. How did they know where to draw those? Well, on your calculator, you just go 3 plus root 5. Like root 5 is bigger than 4, isn't it? Root 4. So that's like 3 plus something a bit bigger than 2 divided by 2. It's obviously positive. This is 3 minus something a bit bigger than 2 divided by 2. You can work out the values so that you know roughly where the roots are, whether you'd put it over there or something. But if you work out those values, you know to draw it there, you know it's concave up. You could even see where the axis of symmetry is. Now that's what you were doing last, well, we were doing more than that. That's what you were doing before. Now in this second example for that polynomial, they're saying show that x minus 1 is a factor. Do you remember how to do those? What do you put in? Negative 1 or 1? Yeah, you substitute 1 in. So to show that x minus 1 is a factor, you do p of 1. And when you do p of 1, you have to get 0. So they put 1 into the equation. They show it's 0 so that we can say x minus 1 is a factor. Now, we're not doing this now. We're just going over what you know and what you've seen before. Then, to find the other roots, you do your long division. Do you remember that? It's a cubic, so we're expecting 3 roots. So when you do the long division, you end up with x squared minus x minus 6. So girls, you know, see what I've highlighted there? If I say write px as a product of its linear factors, that highlighted bit is not linear factors. One of them's a linear factor, x minus 1 is a linear factor, but x squared minus x minus 6 is a quadratic factor. So you have to factorize x squared minus x minus 6 to give you x minus 3x plus 2. So now this is as a product of its linear factors, okay? So once you've got your linear factors, you put it equal to 0 and therefore you write down what the roots of the equation are. And they're all single roots. See how I've got all linear factors here? See, none of those are double roots. They're all single roots. They're not double roots, they're not triple roots. So when they cut through the x-axis, they just cut straight through. Okay, they don't bounce off and there are no inflections. So therefore there are 3 roots there, negative 2, 1 and 3, because there's your roots there. And to see which way you draw your graph, there were a few ways that you could have looked at it. What's one way? It's a positive cubic. What's another way? You can substitute a value. What about the y-intercept is? 6, so we know the y-intercept's there. You could substitute, say, x is negative 3 and see whether the graph starts down here or up there. And if you know it starts down there and you know it cuts through 6 as well up here, it's got to go like that, and like that, because they're all single roots according to this. If one of those was a squared, it would bounce off one of those numbers, or whichever one it had the squared on, all right? Okay? So those are all single roots. Now, what we were doing last year, you could always factorize the polynomial. But this year, we're looking at polynomials where you can't factorize the polynomial. Here's another example. They're saying use stationary points to sketch that curve. and use the graph to give a rough estimate of the roots of that equation when you put it equal to 0. How would you do that? Use stationary points to graph that curve. How do you find stationary points? For stationary points, all right, so they're doing dy dx, right? They put it equal to 0. When you put that equal to 0, tell me what you know you can do straight away. To make your, you can divide by 6, good, or take a 6 out. So for stationary points, dy dx is 0. So we've got that equal to 0. They're dividing through by 6. They're factorising. We know we've got stationary points at x is -2 and x is 1. When x is -2, they're working out the y value, which is 25. When x is 1, they're working out the y value, which is -2. So we've got 2 stationary points at -2, 25, 1, -2. You've done all this before, but this is not what we're doing in this exercise. Then they're doing the second derivative. Why? To determine the nature of the stationary points, they substitute in the x value of -2 here. They get a negative second derivative concave down. Therefore, you've got a maximum. And at the point 1, -2, they end up with a minimum. So the thing is, you can't actually factorise that polynomial if you try. So what they've got a maximum at -2, 25, and they've got a minimum at 1, -2. If you look at the equation up here, the y-intercept is 5, and so that's how you would sketch it. Now, how many roots are there to this equation? Yep, 1, 2, 3 roots to this equation. So there are 3 x-intercepts, so we've got 3 roots. We know that one of them is less than -2. The other one is probably, if this is 1, 2 here, the other one's probably is between 0 and 1, and the other root is bigger than 1. All right, but you don't know exactly where. All right, now, today we're going to look at methods for approximating those roots that we can't factorise. Do you get what I'm saying? All right, so there are 2 iterative methods of estimating roots of polynomial equations that we'll look at. One of them, which is what we're doing today, is called halving the interval, and it's quite simple. It's just a matter of substitution and halving the interval, as they say. And the other one, tomorrow, we'll look at Newton's method of approximation. That involves differentiation, okay? So we use those methods to find the roots of functions these methods can also be used to find the roots of functions that are not polynomials. Now, polynomials have to have powers of n that are positive, all right? So you can use it for any function, in other words, any type of function. So you can find the roots of any type of function, even if it's not a polynomial. Back when we did polynomials, a polynomial was defined as a x to the n plus, you know, b x to the n minus 1 or whatever, where the n's, they had to be whole numbers. Yeah, positive integers, where all your powers had to be positive integers. That's what polynomials are. So you can do this with y equals the square root functions. You can do it with log functions, functions with e in them, which you'll learn about next term, okay, next year. So they can be used with any types of functions, all right? And also they can be used with polynomials that can't be factorised. That's what it's all about. Okay, now, here are 2 functions. It does not matter what these functions are. First method is halving the interval. So here is one function of x, just looking. You don't have to copy it. Here is one function of x. And here is another function of x. Girls, we can definitely say here, they're continuous because there's no gaps in them. And there is at least one root in the interval from a to b. Now, with this first function here, you could say that the root lies not only between a and b, but between 0 and b. Got it? Over here, there is a root between a and b, but we can also see that the root is definitely between 0 and b. Okay, so if function of x is continuous from the values of x lying between a and b, and if function of a and function of b have opposite signs. Now, what does this mean? Function of a and function of b have opposite signs. If I put the value of b, let's say it's 3, into the calculator for that function, would I get a positive or negative value? A positive. So when x is b, y is a positive value. Can you see that because it's up here? But what about when x is a? Y is a negative value. This is what they mean by function of a and function of b have opposite signs. What they're saying is if that occurs, if function of a is, say, negative here and function of b is positive, then somewhere in between the function will be 0. Function of some value will be 0. Okay, same with this one. Function of a is positive here. Function of b is negative here. Somewhere between a and b, that function passes through has a y value of 0. Got it? That's what this is about. Now, it doesn't mean that there's only one root between a and b. Looking here, function of a is positive or negative? Negative. Function of b is positive. In this case, we've got how many roots between a and b? 3. Look, 1, 2, 3. Which is why we say if function of x is continuous and function of a and b have opposite signs, there is at least one root. Do you understand why they're saying at least one? Well, in these two cases, there's only one root. The graph only cuts the x-axis once between a and b. But in this case down here, there are 1, 2, 3 roots between a and b. All right? Now, notes, you can do notes later. We'll just do the examples, all right? If you want to leave some room, what I would do is probably copy this page here that I'm doing now, but don't do it now. Do it at home, all right? I'll just go through it. You can copy it later, leave some space, whatever you think. Now, the way we find the approximation to the root between a and b is by halving the interval, the most simplest method. So here, is function of a negative or positive? Function of b is positive. Look, in this case, it just happens that a plus b divided by 2, which is the midpoint of a and b, happens to be the root of the equation. But girls, that's not always the case. It's actually rarely ever the case. All right? So here, function of a is negative, function of b is positive. We've got 3 possibilities. That exactly halfway between is your root. That the function of a plus b on 2, in other words, the midpoint of a and b, is exactly where your root sits, equals 0. All right? That will rarely happen. What will happen is one of the other 2 cases. Tell me about function of a here, negative. Function of b, positive. Here is function of the midpoint, a plus b on 2 is here. What's a plus b on 2? Positive or negative? Negative. So therefore the root lies between a plus b on 2 and b. Got the idea? Why? Because the value of the function's negative here. The value of the function there is positive. To go from negative numbers to positive numbers, you have to pass through 0. The function's negative, now the function's positive. Got a positive y value, sorry. The function here's got negative y values, the function here's got a 0 y value, up here the function's got positive y values. So somewhere between a plus b on 2 and b, you have the root to the equation. And in the third case, here is function of a, it's negative. Function of b is positive. There's the midpoint, a plus b on 2. But a plus b on 2 is positive or negative? Positive, therefore the root lies between a and a plus b on 2. And that's all. It's sort of like a common sense thing. Okay, the value for a plus b on 2 here is positive. The value for function of a here is negative. It's the function of those. So therefore, somewhere in between is the root. Okay, I think if we do an example, it'll be better. Now, girls, sometimes you don't halve the interval just once. You might have to halve it 2 or 3 times because they might want you to find the root to 1 decimal place or accurate to 2 decimal places. So you may need to do this process more than once, okay? So if we halve the interval several times, the approximation to the root will usually, but not always, be more accurate. It depends if you're moving towards the root or away from it with that case. I'm sure there will be a question that we will do where our root will end up being less accurate. All right, now let's look at these examples. Don't write them out. What we'll do, we'll write out some of the questions from the exercise. Here's our first question. Show that a root of this quadratic of this polynomial lies between 4 and 5. So what they do function of 4, just watching, they get a negative answer. They do function of 5, they get a positive answer. Now, because function of 4 is a negative answer, watch what I'm doing, function of 5 is a positive answer, therefore the root must lie somewhere in between 4 and 5. Okay? Then it says, by halving the interval, show that the root lies between 4.75 and 4.875. So what would be the first halving of the interval? We're starting with 4 and 5. We need to do 4.5 next. And what we're going to do, see, that's just a sketch. I'm not actually sure. That's actually sketched incorrectly. They don't know where that root actually is. But we're going to halve the interval, look at 4.5. So let's look at the function of 4.5. If you put that in, you get a negative answer. Now what I'm going to do, I need to write these down now. All right? Because you can't see what's happening anymore. So what's function of 4? Negative. Function of 5 is positive. What I'm going to do, I need this screen to be, can you still see or no? All right, it's down here. Function of 4 we know was negative 19. Can you see it? Yeah. Function of 4.5 is negative 9. Can you see that? Down here roughly. Function of 5 was positive something, positive 6. If function of 5 is positive 6, function of 4.5 is negative 9, doesn't the root lie between 4.5 and 5? See, it lies between where it's negative and positive. Because if I try function of, say, 4.8, I'll get something very close to 0. So it obviously doesn't lie between 4 and 4.5 because function of 4 is negative, so it's function of 4.5. All right, now what would I do to halve? To get a better approximation, I need to now look halfway between 4.5 and 5. What's halfway between 4? So we look at 4.75. Now we know that the function of 5, I'm just going to write it down, was 6. The function of 4.5 is negative 9 roughly. We're going to now look at the function of 4.75. Function of 4.75 is also negative. So now let's look at it all again. Whoopsie. Oh, back down here. I think I'm on the wrong thing. Here we go. Oh no, I've got to click on the page. Here we go. So we've done... So girls, function of 4 we know was negative whatever. Function of 4.5 was negative 9. Function of 4.75 is negative 2.2. It's also negative. It's not drawn to scale, but it doesn't matter. Function of 5 was 6. Can you see now that the root lies between 4.75 and 5? Now, let's get a better approximation again. So now, halfway between 4.75 and 5 is 4.875. Put that into the calculator and you get 1.686. Now that's above the line. So it's therefore, if it's above the line, let's look at that again. We're looking. Here we go. We know that one was negative. This one's negative. 4.75 was negative, but 4.875 is positive. So it's up there somewhere. The function of 4.875. Function of 5 is positive. Therefore, the root is here. Therefore, the root lies between 4.75 and 4.875. Now, we have to see which one... Sorry? You could halve it again. Yep, you can keep going if you want. But now, it says... Could you ever find it doing this method? Yeah, after about 10 goes. Now, so girls... Now, what's it saying here? It's saying that 4.875 is closer to the 0 than 4.75. Let's see what they mean by that. Function of 4.75 is negative 2.2, right? So it's 2.2 units away from 0. Function of 4.875 is 1.7 approximately. So isn't 1.7 closer to 0 than negative 2.2? So that's why they're saying that the function of 4.875 is closer to 0 than the function of 4.75. Because look, 4.75's value is negative 2.26. Function of 4.875's value is 1.686. It is closer to 0 than 2.2, than negative 2.2. So therefore, it's saying that 4.875 is a better approximation than 4.75. Okay, now, looking at this. I'm just going to go through it, and then you should be, you understanding it, you can follow the examples. This is not difficult, all right? So let's look at this next example. Here. I'll just click on the page so I don't lose it. Next question, example 2. Show that that polynomial there to the power of 4 has a root between negative 3 and negative 2, and use the method of halving the interval to show that the root lies between negative 3 and negative 2.75. All right, function of negative 3, they get 26. I'm going to write these down. So function of negative 3 is 26. Function of negative 2 is negative 33. So in your conclusion, you must write it like this. Since function of negative 3 is positive and function of negative 2 is negative, the root lies between negative 3 and negative 2. Do you get that? All right, so you've got to cross through 0 at some stage between those. Next, we have the interval. What value will we do? Negative 2.5. So we do the function of negative 2.5 and we get negative 21 approximately. Again, sketching out, having a look, you don't have to sketch it. You just have to do the ones that you can do a very quick sketch on the side. It doesn't have to be accurate. Function of negative 2 was negative 33. Function of negative 2.5 is negative 21. Function of negative 3 was positive 26. So can you see it lies between negative 3 and negative 2.5? So we do another approximation of negative 2.75. Substitute that in and we still get a negative answer. So we know that function of negative 3 is positive. Function of negative 2.75 we're getting is negative. So therefore, since function of negative 2.75 is negative and function of 3 is positive, the root lies between negative 3 and negative 2.75, and there is a quick sketch there. Again, to see which one it's closer to. Function of negative 3, we got 26. Function of negative 2.75, we got negative 3. Which one's closer? 26 or negative 3? Yeah, so function of negative 2.75 is closer to 0 than function of negative 3. So therefore, negative 2.75 is a closer approximation to the root than negative 3. Yeah. Look, we'll do some past. I could only find 2 past HSC questions on this. They don't tend to do. It's always Newton's method, the next one. There is one halving the interval method in the last 10 years. All right, so you do tend to get Newton's method of approximation, okay? So, girls, it says this does not always happen. Sometimes the first or second value of x is can actually be closer than the other ones that you find, all right? So, girls, I'll just set you some of those questions for homework from exercise 9.1. We're not going to bother with question 1. Actually, you can do question 3 and 4. So, exercise 9.1, question 3 and 4. Don't worry about 5. Let's look at some of these. What about something like 9? Oh, and I'll also like you to do 6. 6 and 9. So 3, 4, 6 and 9. Ah. Wait, we're not finished. And you can do 11 onwards. Yeah, because they're all 11 onwards. Because girls, do you know how to put an LN into your calculator or not? 11 to 15. 3, 4, 6, 9, 11 to 15. 3, 4, 6, 9, and questions 11 through to 15. Now, I'll just put that up. Homework, exercise 9.1, question 3, 4, 6, 9, 11 to 15.